This is a follow-up from the serial interface demo, this time using PleX to drive it instead of Forth. And just a small correction from last time. I mentioned that spare aux-out pins could be used as reset signals for 4-wire SPI devices, implying that reset was the 4th wire. This is incorrect. The 4-wire protocol uses the 4th signal as a data or command identifier, or DC, for the transfer. Either way, spare aux-out pins can still be used for any of these functions. Later on, I'm planning to demo a 4-wire display which uses both DC and reset. Okay, back to the LED demo. Here's the PleX source code, which is written for the PlasMa assembler. Now, if you want to use my PleX Functions include file, the latest version contains definitions for the new aux and SPI functions and is available on the website under the PlasMa examples section. Links are in the description. You can define your own names, of course. The system calls are all documented in the relevant instruction manuals, so this file is just a convenient way of equating meaningful names to each hex code. I've redefined a few here for clarity. There's absolutely no runtime overhead with doing this. The equates are just used at assembly time. Here are the functions for controlling the SPI signals. There's clock, data out, transfer byte, and chip select. These are the command values for the MAX chip from the datasheet, and the digit numbers for the rightmost 2 sets of 8 LEDs on this particular board. And here are the routines for chip select and deselect, and as in the 4th demo, they're just system calls to set the CS line high or low. And the same for SPI initialization, it just sets the relevant signals high or low. Here's the routine for sending a command. The command and qualifier bytes are passed into the routine via PleX registers, as opposed to the stack in the 4th version. The functionality is exactly the same. Select the chip, do the 2 transfers, then deselect the chip. The transfer return values end up in the same registers, but they are discarded. The write digit routine adds 1 to the digit number to form the command value, and then calls send command. So those are the support routines. Here's the main entry point for the program. We initialize the SPI signal states, then initialize the chip, and finally call a run routine which selects various tests and runs them. I'll assemble the source code. So we have a command window, PlasMa H for the hex file, although I won't be using one of those, but 8 for the 8-bit paper tape file. And using my numbering convention, this one's called 3042, and that's its full name, Test SPI MAX7221 3042. I'm using a batch file to handle this type of format, but that's what you type in using the PlasMa command directly. Okay, I'll copy it to a paper tape SD card. I'm running on Windows, so I need to run a utility called HXD. I'm sure there are others, but this program writes raw format to an SD card. I've showed this before in previous videos. On Linux, you can use the DD command. Anyway, we'll open the device. The SD card's already plugged in, and this is it. Just confirm the size, 240 megabytes. Don't go and overwrite your master disk. Make sure it's not read-only. Highlight it. Double check. OK. Ignore the warning. And that's the original contents of the SD card, which looks like a paper tape, which confirms we've got the right disk. You can now open the file I've just created with the assembler, which is test. There we go, test SPI. PLS was the source code, and it's generated a listing file, a hex file. This is for the simulator, and then an 8-bit paper tape file. So that's the one we want to load. I'll just say open as read only so we don't overwrite it by accident. Open. So we just do Control A, select all, and then Control C to copy. We go over to the SD card, and Control and B writes it back to the card. And we do save. Again, another warning, make sure you don't overwrite your master disk. Yes. And then close. And I think, just to be safe, we do a safe remove. Removable disk eject. And it says safe to remove hardware. So I'll take it out and go and put it in the machine. Okay, here's the card going in the paper tape reader slot. I've already loaded microcode 3. You see 3 on the lights here. This is for PleX. So reset and run. And the bootstrap is waiting for a tape to be loaded. So press load, and there it goes. Right, the tape's loaded, and we're now waiting in the run loop. It's waiting for a user input. Now the native 4th emulation was a lot more convenient here, as I could just enter everything on the keyboard. But to do that with PleX, I would have to write a lot more code. So to keep it simple, I'm controlling the program with PlasMa's switches. And all these switches can be read using system calls. I'm going to use the top 8 of the load switches to define which test number to run. Here's the source code. The run routine reads the most significant 16 bits of the load switches, that's all of these, into register 0. It shifts it right by 8 places to discard the lower 8 switches. And then it does a series of comparisons and jumps to the relevant test routine. Now each routine jumps back to the run routine, so it loops forever. There are no doubt more efficient ways of doing this, but I'll leave that to you. So let's try test 1. This does the same as the 4th demo and turns on LEDs one at a time within the rightmost digit. Now the time between each change is defined by a simple delay loop. Now I could have used more accurate timer functions, but using a crude loop controlled by the switches was more fun. The delay routine reads the least significant 16 load switches into register 3, then decrements it in a loop until it reaches 0. So we can control the speed in real time. So we've just got that one set. Slower. And flat out, and they're all off. Okay, test 2. This spans the rightmost 2 digits. Test 3 treats the 8 LEDs as a counter. Again, we can adjust the speed. See it counting in binary. Test 4. This copies the static values from these 8 switches directly into the LEDs. So if I put all these off, all the LEDs are off, on, let's skip a couple. And test 5 uses the shutdown command, which we covered on the previous demo, and it toggles it on and off, just to show you can use it to flash the display or just leave them off for conserving power. Okay, and finally test 6 just turns all the LEDs off. Okay, that's it for this demo.